Within the Earth's crust, hidden in plain sight, lies an element of subtle yet profound potential. It is scandium, a silvery-white metal, atomic number 21. Though it resides in the D block of the periodic table, it has historically been grouped with the rare earth elements, a family known for its unique and often indispensable properties. Its story is not one of abundance, but of a quiet, persistent presence, woven into the fabric of our planet's geology, and increasingly, into the fabric of our most advanced technologies. The tale of scandium begins not with a chance discovery in a mine, but with a prediction born of pure intellect. In 1869, the architect of the periodic table, Dmitri Mendeleev, perceived a gap in his grand design. He foresaw an element he named a carbaron, an unknown substance that, according to his calculations, must exist. A decade later, in 1879, Lars Fredrik Nilsson, a Swedish chemist, was meticulously analyzing the minerals euxenite and gadolinite, sourced from the ancient bedrock of Scandinavia. Through the precise language of spectral analysis, he detected a new signature, an element never before seen. Unaware of Mendeleev's prophecy, he named it scandium, a tribute to his homeland. It was only when his peer, Pierre de Clèves, recognized the perfect correspondence between Nilsson's discovery and Mendeleev's prediction that the triumph of scientific foresight was fully realized. A ghost in the periodic table had been given form and a name. Despite its theoretical and eventual discovery, scandium remained an enigma for decades, a curiosity locked away in mineral matrices. It is found scattered across the globe, a trace component in deposits of rare earth and uranium compounds. Yet, its extraction is a formidable challenge. The process is complex and costly, and for many years, the metal itself was little more than a laboratory specimen. The first isolation of metallic scandium was not achieved until 1937, through a difficult process of electrolysis. It took another 2 decades, until 1960, for the first pound of 99% pure scandium metal to be produced. For nearly a century after its discovery, its practical value remained elusive, a solution waiting for a problem. The 1970s marked a turning point. Researchers discovered that a minuscule addition of scandium as little as 0.1% could impart extraordinary strength to aluminum alloys. This was the breakthrough that propelled scandium from the pages of academic journals into the high-stakes world of aerospace engineering. Its use in these specialized alloys remains its primary application, a testament to the dramatic impact that even a trace amount of an element can have. Yet, its scarcity continues to define its role. The global trade of scandium oxide, its most common commercial form, is a mere 15 to 20 tons per year. This limited supply has kept it a niche material, a secret ingredient in some of our most demanding technological pursuits. The chemical character of scandium is one of intermediacy, a bridge between its lighter neighbor, aluminum, and its heavier cousin, yttrium. This unique position grants it properties that are both familiar and distinct. Like many elements in its group, its preferred state in compounds is one of stability, having given up 3 electrons to achieve a +3 oxidation state. A more curious connection, a diagonal relationship, links it to magnesium, echoing the similar bond between beryllium and aluminum. These fundamental chemical behaviors are the key to its power, dictating how it interacts with other elements and unlocking its potential to transform them. It is this atomic-level architecture that allows scandium to work its metallurgical magic. The quest to obtain scandium is a global endeavor, driven by a demand that consistently outpaces its limited production. Historically, the world relied on just a handful of sources, byproduct streams from uranium mines in Ukraine. vast rare earth operations in China, and apatite deposits on Russia's Kola Peninsula. In each case, scandium was never the primary target but an incidental prize, painstakingly separated from more abundant elements. This dependency on by-production has created a fragile and often unpredictable supply chain, hindering its widespread adoption. Recognizing this bottleneck, new ventures have emerged, seeking to secure a more stable supply. Facilities in the Philippines now contribute to the global total, and ambitious projects are underway elsewhere. In the United States, a proposed mine in Nebraska, primarily targeting the element niobium, could potentially yield as much as 95 tons of scandium oxide annually. Such an increase would be transformative, potentially lowering costs and opening the door to new applications. But even with these new sources, the fundamental process remains unchanged. The journey from ore to application begins with scandium oxide, which must then undergo a rigorous chemical conversion to scandium fluoride. Finally, in a fiery reduction process using metallic calcium, the pure silvery metal is at last liberated. It is a path of intense energy and chemical precision, a modern alchemy to yield one of Earth's elusive treasures. The most significant chapter in scandium's modern story is written in the sky. Its primary application, by weight and by value, is in aluminum-scandium alloys destined for the aerospace industry. When added to aluminum, scandium initiates a remarkable transformation at the microstructural level. It dramatically limits the growth of large, brittle crystals that can form in the intense heat of welding, a common point of failure in standard aluminum alloys. The secret lies in the formation of nanoscale precipitates of an aluminum-scandium compound, Al3SC. These tiny, orderly structures act as reinforcing pillars within the aluminum matrix. They create elastic strain fields that effectively pin the atomic structure in place, inhibiting the slippage of crystal planes, the very essence of plastic deformation. This mechanism grants the alloy a strength and fatigue resistance far superior to that of aluminum alone. It allows for stronger, more durable welded joints, enabling the construction of lighter and more complex structures without sacrificing integrity. The science of these alloys is one of continual refinement. Researchers have discovered that adding other elements, like zirconium and erbium, can create protective shells around the scandium precipitates. These shells act as diffusion barriers, preventing the precipitates from coarsening at high temperatures and thereby preserving the alloy's strength over time. This innovation also makes the alloys more economical, as less of the expensive scandium is required to achieve the desired effect. The result is a family of materials that begin to rival the performance of titanium alloys, celebrated for their own blend of strength and low weight, but with the potential for lower cost and easier manufacturing. Alloys have been developed that are as strong as titanium, as light as aluminum, and as hard as some ceramics, representing a new frontier in materials science. Beyond the theater of military aviation, scandium's unique properties have found their way into other domains where high performance is critical. Lightweight, high-strength sporting equipment, from baseball bats and bicycle frames to lacrosse sticks, has been crafted from scandium-infused alloys. These applications leverage the material's ability to withstand repeated high impacts without adding prohibitive weight, giving athletes a competitive edge. The American firearms manufacturer Smith & Wesson has also adopted the technology, using scandium alloy frames for some of its revolvers and pistols to create exceptionally lightweight yet powerful sidearms. More recently, the advent of 3D printing for metals has opened another new chapter. A scandium-containing aluminum powder, marketed as scomaloy, allows for the additive manufacturing of intricate, high-strength components that were previously impossible to create, pushing the boundaries of design in aerospace and high-performance automotive sectors. While its metallurgical applications are its most significant, scandium also plays a crucial, if less visible, role in the world of illumination. It is a key ingredient in a specific type of metal halide lamp, a technology that has shaped the look of our modern world. When scandium triodide is combined with sodium iodide inside a lamp's arc tube, it produces a brilliant, high-intensity light with a color spectrum that closely mimics natural sunlight. This high color rendering index is vital for applications where true-to-life color is essential, most notably in television and film production studios, as well as in high-end retail and architectural lighting. Annually, only about 80 kilograms of scandium are consumed globally for this purpose, a tiny amount that has a vast impact on how we see and capture our world. The light that illuminates our screens and stages often begins with this rare and remarkable element. Its contribution extends even into the precise world of modern medicine, where specialized laser crystals doped with scandium are used by dentists for delicate procedures, a testament to its versatility. Scandium's journey from a theoretical prediction to a critical component of advanced technology is a powerful illustration of the scientific process. It is a story of foresight, of patient investigation, and of the transformative potential that can lie dormant within the most unassuming of materials. Its scarcity has long been its defining limitation, a barrier that has confined its extraordinary properties to the most demanding and high-value applications. But as our ability to extract and refine it improves, the prospect of its wider use becomes more tangible. This silvery element challenges us to look deeper, to understand the subtle chemistry that governs our world, and to harness it with wisdom. The story of scandium is far from over. It is a quiet revolution unfolding at the atomic scale, promising a future built from materials that are stronger, lighter, and more resilient than we once thought possible. It reminds us that sometimes the greatest strength is found not in abundance, but in the precise and powerful influence of the truly rare.